inside the unit. So the refrigerant is a tenth of what it might be typically for a standard air-cooled unit. You could go one further, and you could put a permanent run-round coil with separate planting, and then additional pipework, etc. Or you could even put a free cooling chiller on the other circuit, and then have dual redundancy of refrigerant, etc. Again, you've got the facility then to bring in free cooling. So CRAC units provide a very efficient means of cooling IT equipment. There are restrictions on how much refrigerant you can run. There are restrictions where you can place the plant, but generally they will provide an economic solution as long as they can be designed into your systems and the architect systems and everything else. But if you then look at the energy cycle, so we go on to, we then viewed the energy that the standard DX, the DX with fresh air, free cooling, and the DX water cooled would give. And it's not easy to see, but a standard DX unit, typical PPUE 1.21. If you've got the water cooled, 1.11. If you've got fresh air, 1.07. So if you can get away with using fresh air within a CRAC unit, you're reducing the energy input by 67%. So from an energy principle alone, it has a positive payback of a year, 18 months, something like that. There are points to consider. You may all well be aware of all of these. Obviously, refrigerants, there is continuous news about refrigerants and what's happening with them. And again, plant space, noise, and pipework, etc. But our most critical problem at the moment is refrigerants. We use, and the industry uses, R410A, which has got a GWP of 2088. There are restrictions coming in. They are going back. So just like the delay in getting rid of gas boilers in your houses, getting rid of refrigerants seems to be going back in timescale because the products to replace them just aren't there. We use 410A, which has got a GWP of 2088. Generally, if you want to lower the GWP, you either have a less efficient refrigerant that gives you less duty, or you have one that's flammable. And the industry is reluctant to use inflammable refrigerants, but they still want the efficiency. So at the moment, the manufacturers of the refrigerants are having to develop and redevelop a refrigerant with a lower GWP that could still be used in the same basis. The problem that we have is that if you have a low GWP refrigerant that isn't flammable, 40 kilowatt unit becomes a 25 kilowatt unit in the same space because its efficiencies are such. So it has lots of knock-on factors which are affecting the industry in general. And unfortunately, refrigerant prices are rising, and we have everyone on our back from the Green Brigade onwards. Obviously, it is a valid requirement these days to be as green as we can and to have the most efficient, and both in terms of energy and in terms of CO2 reduction that we can. An amusing slide, really, for those who are of an age to remember such installations. I don't know if you can see that from the back there, but we quite often get left with the corner of a space left to put all the heat rejection in. You've seen this before, haven't you? And you'll see it on roofs. Everything is compacted. You're blowing into another unit, into another unit, into another unit. Architects sometimes are lenient and give some space, but plant space is never enough. We would love it to be like that. Nicely spaced out on a roof, lots of airflow. Doesn't always happen, unfortunately. The final issue with all refrigerant products, again, which is something to factor in, is they require oil, and they require that oil to be recirculated in order to protect the compressor, which requires minimum velocities around the system. And we then monitor the pressures that the systems work at to make sure that they're okay, which is great. But we then come to what, have you heard of the CHEWI, total equivalent? It's a factor, yeah, total equivalent warming impact, which basically looks at the life cycle of the product itself as a combination of both the energy that's used, the CO2 generated, and the effect that the refrigerant use has on that product. So this is a 40 kilowatt unit. It's got 15 kilograms of refrigerant in it, factoring in a little bit of leakage each year across its life cycle and a little bit of loss when you scrap it. And then the energy used to run the system. What that says there, 97%, is the CO2 impact of physically running the unit. So the fact that it's got refrigerant in it only accounts for 3% of the CO2 that may be generated by that unit through its life cycle. Now, I say may because if it's installed properly, it's pressure tested properly, you may have zero leakage across a 20-year life. So whether you're using a unit with a GWP of 2000 or a GWP of 1, if it doesn't release, it has zero impact on the environment. However, the fact of the matter is that legislation is driving us as a business to look at removing refrigerants, full stop. So the fact that they don't account for that much isn't being considered as much as perhaps it should be, but it's just a valid point to be made. So what can we do? Well, most manufacturers at the moment are treading water and staying with the 410A that we have done for many years until a better product comes along. We can use drop-ins. We can change to other refrigerants that give you a lower duty. We can change to refrigerants that are flammable. Neither of it's perfect. We can move away from DX in total. You can put in chillers. The chillers, okay, yeah, they've got lower GWP refrigerants. They're outside. They are flammable. Doesn't matter as much, but you've got issues with noise and everything else that comes with chilled water. But more importantly, will it then mean that free cooling becomes obligatory? Possibly so. So if in your IT installation you can't use a CRAC unit, then what can you do? Well, if you're a hyperscaler, you'll be using fan wall technology, which is basically, if you imagine the old kids' toys of stipple bricks, and each brick is a fan, a coil, and a filter, and you just combine them together and make them as many as you want. We do them in configurations typically up to 9, which can be up to 900 kilowatts of heat rejection, or cooling, should I say. They're installed into the hot aisle. So your hot aisle enclosed environment. There's no refrigerant. They're connected then to dry coolers on the roof, which may or may not be adiabatically cooled, which is another factor these days for your WE to be considered, but there's no refrigerant in them. So in terms of free cooling, once these start running at higher elevated temperatures, you can apply free cooling by the means that you reject that heat. And we've recently been doing a job with one of the big boys in America where they've built them into containers. So the cooling plant is placed underneath the IT and then blown into the IT from underneath. The big change in the industry, I don't know whether you've come across liquid cooling at the moment and seen it in all the trade press, and it's everywhere you go on LinkedIn, it's liquid cooling. So there are a number of different options. You've got people that will do what looks like a chip shop fryer and your servers are immersed into fluid. We use a spray system. So this is our product, and what we do is we spray the server. So if I go through to there we go. So what we do is we're spraying the server with the dielectric liquid. It runs over the CPU, drains down into the bottom of the unit. So they're not immersed. We've actually only got about that much of liquid in the bottom of the drawer. The drawer pours out. You've got 7 2U servers, 7 in the top, 7 in the bottom, 14 in total. You can reject 50 kilowatts or so of IT load within that one cabinet, which is sort of the same size as a rack within a computer room. What you're doing then is you are linking that dielectric fluid through one half of a brazed plate heat exchanger. On the other half, you've got, again, water pipework going out to a dry cooler. So you are directly rejecting the heat from the CPU into the dielectric and then cross into condenser water, taken away. The dielectric's running at anything up to 60 degrees C, which is very efficient, which means that your heat rejection plant is quite small compared to the load that you're actually rejecting. But more importantly, you've got potential to recover heat from that before you reject it outside. Secondary heating within a system, domestic hot water, underfloor heating, something of that instance. There are various schemes going on. People have used it to heat swimming pools, commercial greenhouses, that sort of thing. The problem in the UK historically is that data centres have never been built around large-scale housing developments. So in Europe, they use a lot of the recovered heat for district heating schemes. The UK, it's more difficult, so they are sort of starting from scratch as to how they apply that heat. But the principle remains that by using liquid cooling, you have the facility to A, get rid of any other form of cooling. You don't need CRAC units. You don't need big air handling units to cool the white space, cool the IT load, because it's all being directly taken from an enclosed environment and removed out. You may get a little bit of radiation from the box that the servers are in, but that's about it. So this then negates any use of refrigerant, and neither do you need to use adiabatic spraying of the dry coolers outside. They will work up to 50 degrees C before you need to enhance their performance. So anywhere in Northern Europe and even North America, then they will work without refrigerant, without water. So it becomes a very efficient solution. It's a product that's in its infancy, and it's being marketed across the world really by various people, because ultimately this is probably going to change the way that IT is cooled and move it into smaller facilities with multiple of whatever they be, whether they be drawers, whether they be chest freezers with dielectric fluid.
When you say dielectric, it's water.
It's an oil. It's an oil. So it's and you've got people like Shell and all the oil companies. They are now developing dielectric fluids for the liquid cooling industry. Ultimately, what you will have is you will have Dell, because its server is the main issue. Dell will not warrant their server unless it's used in a correct environment. So we're doing trials across the UK, and ultimately Dell will say, we warrant our servers within X liquid cooling machine using Y dielectric. And then if you tick that box and tick that box, you get your warranty from Dell for that server used in that environment. And this is the way that the market is going to is being driven, because the Dells of this world and all your other server manufacturers, they are the ones ultimately that are the puppet masters.
And how we pull the rack out from the data center, so it will all be wet.
Well, this because when you're immersed, you lift it up, and it is slightly oil. It's a thin oil.
So it will drip off.
It drips off, but you have to then leave it to drip, and it can be messy when they're fully immersed. Ours, basically, it's inclined at about a 30-degree angle, and it's sprayed and it runs down. So you're only really spraying the bit that's hot. You can then turn off that sprayer for that one particular server, extract it, so that it's proud of the draw. It'll run off of 10 minutes. Then you can remove it, do what you need to, put another one in. The other 6 in the drawer are still cooling. You don't lose cooling to the other 6 by taking one out. It still carries on. So it's a very novel solution. And they're all very simple, really, in terms of it. The technology is the dielectric fluid being stable over a period of time, because it's about $25 a litre, and some of these installations have 500 or 1,000 litres of dielectric in them. So that's $25,000 before you start. So you don't want to be changing that every year. You want to be able to clean it and reuse it. So a lot of these manufacturers of the dielectric currently are testing the long-term efficacy of their particular product in the marketplace. So in about 3 to 4 years' time, I would suspect that will then be coming across the industry.
So it's conducts heat.
It conducts heat, but not electricity. No. So you could put your finger in it, and you'd get a dirty finger, but you wouldn't kill yourself.
You get burnt.
No, it's at the dielectrics at about 50, 60 degrees. Well, in theory, yeah, 50, 60 degrees C. The CPU is at 80, 70, 80, something like that. But the dielectric, it's hot, but you won't burn yourself. No. So it.
I'm shocked.
And when you look at the overall efficiencies of all the established means of cooling IT, liquid cooling 1.03, all the way up to traditional old-time legacy equipment, which can be up to 1.5. So half the energy used in the facility is for your cooling. With liquid cooling, it could be 3%. And if you start to recover the heat from the dielectric and use it for low-grade heating within your building, you can get a PUE less than 0, less than 1, so to say. So 0.95, 0.97, something like that. So the future is very rosy, but it's if you remember the analogy of VHS and Betamax with the old videos, that there were 2 or 3 different. They were vying for superiority, and the best way to do it. We're in that stage at the moment. So,
in terms of the dielectric type, or in terms of the other system,
it'll all be dielectric, but it's whether it's fully immersed, whether it's sprayed. There are some systems where literally they have tiny pipes spraying into the CPU. So literally it's closed circuit, so the CPU is dry, but it's a little bit inside. So the server is dry, but the CPU itself is enclosed.
Detail on top of it.
Yeah, and but then all the heat then it's not just the CPU that generates heat in the server, that you get another bit of other heat off it. So you then still got to cool the air in the room. So that bit is you still then need two cooling sources in order to achieve. So
what would the second cooling source be?
sorry?
You said in that instance you will need two cooling sources.
Well, yeah.
What would the second one be?
So if you've got an existing computer room with a raised floor and downflow units and servers in racks, the downflow units are sized for all your heat loads within the room. 99%, 98% is your servers. You've got a little bit of lighting, you've got a little bit of ventilation. If you use immersed or spray cooling, then you're removing 99%, 98% of the IT load from the actual server, chucking it outside, but you get a little bit of radiation. So our unit will remove, say, 50 kilowatts of heat load. You might get 1 or 2 kilowatts of heat radiation from it. Then you've got your lights and bits and pieces. So whereas if you've got a computer room with 1,000 kilowatts of IT load, you might find instead of having 100 kilowatt CRAC units to give you an N+2 environment, you've put it all onto liquid cooling, and then you've got a couple of 20 kilowatt CRAC units just to do the little bit of heat that's rejected by the devices. But the majority of it is then gone outside by the heat exchange. So it depending on where you are and how much heat load you've got there, you might find that it's very small indeed, the amount of additional ancillary cooling that you might need. We can then move on to techniques that combine fresh air and refrigerant as a means of cooling, and we make a variety of products. One of which is this, which is called the Unicool Edge, which is a new product, but basically it's a combined fresh air. Do you remember the Eaton Williams units, BTX units, and
I think that's Jan.
Yeah, you had fresh air and DX in a combined one box. You put it against a wall, and it would bring fresh air in, and if the fresh air was hot, it would put the DX on instead. Yeah. So that's mature technology. We still make those units. They're on a couple of slides later. Very good, work very well. Take the philosophy one step further, put it on its side. You've then got this unit, and what this enables you to do is to if we skip through, what this allows you to do is to give you a cold R segregated environment in a cabin or a room. It doesn't have to be a cabin. So the unit will blow fresh air down one side, extract hot air down the other. It can be stacked. It can be stacked at each end. So you can take a cabin and have 200 kilowatts of load in a cabin and put a true cold R container, which you've not been able to do so far. The traditional vertical style units would only supply air in one direction and it extract above it. So unless you use a raised floor and tiles like in a traditional computer room, it meant that you couldn't get that airflow efficiently around the facility. And as I say, you can then zone them, you can then make them bigger, you can combine them. And essentially, if you've got a warehouse that's a data center, you can put these sorts of products along the outside wall and create banks of cooling that align with the cold are contained racks inside. So it becomes a very efficient system as long as you've got the facility to get that fresh air into the room. Okay. So this sort of product, originally developed in the United States for a company called Lighton. It'll work up to 50+ degrees C. It'll work down to -35, and at all points in between. Obviously, it's not going to give you fresh air free cooling at 55 Celsius, but the refrigerant will still run as it will down at -35. On a simpler basis, we then have the more traditional vertical style fresh air DX units. We call them FADX. It's a terminology in the industry, much like calling a vacuum a hoop, for example. And again, the same principle applies, where you either bring fresh air in from outside to do your cooling, or you can bring DX in, and it will modulate throughout the year the most efficient. And these are traditionally used in exchanges, equipment rooms, UPS rooms, that sort of thing. And we can put them on the outside again. So they will sit on the outside and do exactly the same manner. In terms of installation, for any of them, you cut 2 holes. You bolt the unit onto the wall, you seal it up, put refrigerant in and power, and off you go. There's no pipe work. So they're installed in a day. So very efficient. This is a particular example at a BT site, as you can see on the cabins. And sure, if you drive around through any industrial estate or whatever, you'll see them in fields and the backs of buildings. And we do versions that come with inverter compressors and versions with fixed speed compressors, dependent upon the budget of the client. As I touched on earlier, one day refrigerants will be banned, disappeared, unless they change their perspective in the years to come. Evaporative cooling then becomes a means that you can provide reasonable cooling to a degree throughout the year. We make a particular product called the AD. The principle is I'm sure you're aware of, the evaporative pad and blowing air across it. So basically, we have a nice little pad and our warm air going across, and some water, some nice cool air going into the room. In terms of efficiency, where we are, very good. We'll get up to 80–90% RH off it. Works well in hot environments as well, obviously. So in terms of the psychometric principle, we are adiabatically cooling up the wet bulb line to approach the saturation line, but not completely. And in terms of the operation, we are, again, similar to the other units you saw, where we are bringing fresh air in and we are cooling it via the pad, or recirculating air and mixing it as required. And this particular sort of product, again, would sit inside the room. You've seen the earlier example with the CRAC unit, and air in and air extracted. Reasonable expectations with evaporative cooling in general, and the European climate, is 98% of the year you should be able to achieve 21 degrees. If your client's got strict SLAs and they want 21 ±2, and they want 50% RH ±5, you're not going to get that with adiabatic cooling of any description. You're not going to get that with fresh air. So this one point, as I made earlier on, if the clients are particularly finicky with what they want to achieve, then the type of product that suits best could be one that's far less efficient. but it's guaranteed. So there is this assessment process. Part of what we offer to yourselves is we can look at the heat load that you've got and what your client expects, and come up with A, B, C, D, E, and the various merits and disadvantages of each, the energy of each, etc., so that you and they can form a considered opinion that in their circumstances, that CRAC unit would be better than that package unit, for example. So that takes a lot of the hard work out of the thought process from yourselves, from designers, from contractors, and then the client can then decide whether he can actually afford what it is that achieves what he wants. And then value engineering comes in and he chooses something else that was a little bit more affordable, but doesn't actually give him what he wanted in the first place. So we play that game all the time, unfortunately, but it's interesting to see the analysis. So something to bear in mind. Certainly in terms of installing the adiabatic systems, it's a water supply and it's a drain. It's as simple as that. So in terms of energy, really it is just a fan. There is a little bit of water. You can lower your electrical demand on the room. Now, BT use these extensively. And what they do is they remove a DX unit. They put an adiabatic unit in. They release a few kilowatts of heat, of energy that they can then put some more surface in. Basically, so they're not saving themselves any money, but that just means they can sell a bit more space to their clients. So there's no refrigerants, so we don't have to worry about the ozone and the GWP. There is a water usage. It's a calculated amount of however many meters cubed per annum. It's not that huge in comparison because we only bring the adiabatic function on when the ambient temperature goes above a certain level. So if it's Scotland, it's far less than the affluent south, should we say, where it's warmer. Okay. We did a recent example of energy usage of these two units versus, and I can't read that. So with 55 kilowatts of load, 2 of the adiabatic units versus 2 DX CRACs, and the adiabatics were £500 odd to run for the year. The 2 CRACs were 10,000. Now, I do stress the point that the CRACs give you 24/7, 365 guarantee of conditions at all times, whereas the adiabatic has a small limitation 98% of the year. But in terms of an example of energy efficiency, there's such a huge dissipation between the two that it's when refrigerants are restricted, this sort of technology will become much more prevalent. In terms of Legionella, it's all tested and certified and has been used for many, many years. So if it ever is raised, is there an issue? The answer is no. And
the temperatures they're working on, it's quite within the range of Legionellas.
Yeah, the water is so it's only really running when it's required. It's reused and dumped, So the pan is regularly dumped. There's no stagnant water lying around within the system. So it conforms to all the regulations for preventing Legionella.
It's going to be around in that temperature range you're looking at.
Well, we are so when we are, I think it's above 22 degrees C, 22, 23 degrees C ambient, we start to run the water through the media, but we are evaporating pretty much up to saturation, a little bit below. So there's very little that actually is not evaporated. There's a little bit that's collected in the drain pan, which can be then reused, but then it is dumped. So there's never anything left long enough that attracts Legionella.
When you say it's dumped, that means it's disposed, drained off.
It is drained away. Yes. And when the when it's in operation, you have this system of use, recycle, dump. When it's not calling for the water, the valves are shut off and the drain pan is dumped. So it's only, there's only water in it when it's being used, and then it stops and drains away. So yeah. And then finally, we have just fresh air, which, you know, in this country, fresh air will give you free cooling and cooling for a large percentage of the year. Again, it is not guaranteed. Now, for example, BT will put one of these units in, typically a 2 meter cube a second unit. But what it means is that in winter, it brings fresh air. But in winter, it can nigh on replace the use of a CRAC unit. So it almost becomes a priority cooling. It then backs off the refrigerant in any other unit and then saves them the money. During the summer, obviously, it is then just bringing fresh air in for occupancy. So it'll work on a two-foot basis. And they go down to a very small size, up to 20 or 40 kilowatts. Yes. Are there any disadvantages when you're using fresh air, particularly fresh air for free cooling? A lot of people say that you bring in contamination, fumes, smoke, humidity, and do you get lack of control? Now, the honest answer to that is, if you look at people like BT and others, they have used fresh air for decades with very little effect on the IT equipment that they use. We've got installations in the Channel Islands where you couldn't get much worse conditions, and they have no issues. If you're thinking of fumes, if you're thinking of pollen, smoke, heavy rain, we sense for all of those aspects, and if it's prevalent, we close the dampers. So if there's a rainstorm outside, if it's a site next to the fields and they're cutting the rapeseed or whatever, and you've got all the dust everywhere, we close the dampers. So it's foreseen, it's taken aware of, and it's prevented. The only issue with fresh air is you are restricted in controlling your humidity levels within the space. And to add to that, most server technologies these days aren't really worried as long as it's between 20 and 80% RH and isn't fluctuating too quickly. So when you're bringing in fresh air in the winter, because it's cold, you bring less fresh air in, so you're not introducing as much low humidity air. So is it a problem? No. In reality, you could humidify if you wanted to, but that then negates any of the energy savings you're getting by running fresh air. So in reality, if you're going down the fresh air route, then humidity control tends to be relaxed, shall we say. You won't get 50 plus or minus 5 whilst you're controlling with fresh air, for example. But most IT companies these days and data centers really aren't that worried about the RH, as long as it's not so low as to cause static. So in other words, no, we don't believe that there is a risk, and where there is, it's engineered out by good design. We've rattled through that. That's good. And I say, hopefully that hasn't, confused, baffled, or told you things you already know. But basically, we are Airsys. We manufacture these products which are installed into the UK market, some of which are unique to ourselves. So the fresh air CRAC, for example, is a unique product to ourselves. The spray cooling is unique. The horizontal fresh air DX unit is a unique product to Airsys, which we apply into the market and give, right at the end of the day, what he needs, which is the economic, efficient cooling of their IT load within a reasonable footprint and to their expectations, which we can ask no more, basically. And really, that's where we are.
One interesting thing is when you're in a situation where the humidity is, you've got rain in Manchester, for example, when your humidity is about 90%, what do you then bring into enclosure?
Yeah, I mean, in terms of if it were CRAC technology, for example, we can dehumidify a standard by purely using the refrigerant coil to reduce the RH. Now, typically we see conditions go up to 65 or 70%, 75 perhaps. You get a natural cooling effect across the coil anyway, which will, if it's very humid, which will reduce some of that humidity out. But if we need to specifically dehumidify, then we normally drop the airflow across the coil a little bit and reduce the sensible heat ratio, sweat some moisture out in that respect. So if you're 50 plus or minus 10, something in that order, then standard refrigeration CRAC unit technology is perfectly okay. We've gone down as low as 35% RH with our CRAC units. We can alter the superheat for the coil. We could drop the evaporating temperature. We can engineer how it works, and we can you get to a point where it's probably easier to use a chemical dehumidifier to get down to those low levels than it is to use a CRAC unit, and it depends for the duration that you need to be down there, for example. But typically 50 plus or minus 10 with a CRAC is a nice economic position to be. If you're dealing with fresh air units, now the time that you've got high moisture content in the air rather than high relative humidity is during the summer months, where you're not using fresh air to cool the space. You're in recirculatory mode and using the DX. So the same principle applies. That DX is then naturally dehumidifying the air and keeping you down within that 40 to 60, 40 to 65% RH band that you'd like to be in anyway. When you're in the winter, your moisture content is lower, your RH is higher because the air is cold. So you then, by the time your fresh air is in and warmed up by the IT load, you're typically then down around the 25 to 30% plus RH level, which again is within the limits of the server technologies. It's not down to 10% or anything down like that. We can limit the temperature of the supply air into the space. It's difficult to limit the moisture content of the air into the space. But you do tend to find, as I said earlier, that as the air is colder, you naturally bring less of it in to get the same amount of cooling. So it sort of balances itself out a little bit, that you're bringing in less but drier air versus more but slightly more humid air as the temperature increases outside. So humidity doesn't tend to be an issue. The only time we've had issues with humidity is where the client has a precise RH requirement, and that's typically only in clean rooms or standards rooms where they want 30% RH to manufacture their powders. And in those instances, a chemical dryer is a much better option in terms of the energy but you'd have a chemical dryer with some form of cooling a CRAC unit as a combination, for example.
How do you do with filtration of pollution?
Sorry?
Pollution, air pollution.
Well, I mean, it depends where you are. I mean, we sense, as I say, we can sense smoke outside. You can fit sensors that sense diesel fumes, that sort of thing, and we can then close the fresh air dampers. You find it in industrial estates where you backed onto a trailer yard somewhere and you've got high levels of diesel fumes. So yeah, you back off the dampers. In those situations, we probably look at it twice and say, do you know what, you're going to suffer this frequently. It might be better to look at some other form of cooling that still has free cooling, but it's indirect, for example, and then that might be a better way of doing it. So we try and capture all those eventualities where we can, but where it does happen and where it's unavoidable, then yes, we can sense it and close the dampers while it's being caused. We find it quite often where there's torrential rain, and you'll find that it's bringing in fresh air. And that torrential rain, you got the risk of bringing the water in through and into the room. So we close the dampers off, and we just bring the DX on while it's raining. So for the 2 or 3 hours that it's happening, it's really not that important in terms of the energy cycle, but it does prevent any water getting inside.
I'm just dreading of a machine room where you go in there and you can just do that all the time.
Yeah, I'd say, I mean, fresh air isn't perfect. Fresh air is great, and in terms of if you're looking at, if your driver is reducing the energy to the absolute minimum that it can be, then fresh air is perfect. And now I've seen sites where you've got salt corrosion, you've got pitting because it's coming in off the sea. You've got, as you say, you open up the unit and it's got water everywhere, or it's got dirt, you've got bugs, you've got all manner of things. We cannot overemphasize the need for regular maintenance. Now, unfortunately, clients aren't the best at having maintenance schemes in place. They wait till it breaks down and they wonder why the filters have gone like that, and or they've even disappeared, and then they wonder why it's not doing the job.
Yeah.
We do planned preventive. We give them a heads up. You're going to need to do this next time we come. We clean out inside and we come back next time, and we clean out inside and we come back next time, and we clean out inside. So it does need to be done, and it needs to be emphasised to the customers that it's in their interests. It's their unit. It will last them 20 years, or it'll last them 5. Do as you want. But certainly, we've recently done JLR Halewood. We've changed 2 of their data centers. So one data center, we've now got a load of in-row units inside the racks, and another one they've got conventional perimeter CRAC units. But they're working very well. Nice standard technology. In that instance, they weren't worried about free cooling. They just wanted straightforward DX. If you look at old traditional legacy DX, where it's fixed speed compressors, fixed speed fans, just by putting in a new inverter regulated DX unit with no free cooling, you have the running costs just by doing that. You put it with free cooling, you can quarter it. So, it depends to what extent you go, but just by putting in efficient technology, you save yourself. So
it's most times you go for new installation.
Well, there's a lot of people have already changed fans to EC, dependent upon the units that they're being. Certainly, there's still a lot of work going on with their handing unit central plant, where they're changing old belt driven fans, putting in fan walls, for example. In terms of CRAC units, the problem is a 25-year-old CRAC unit will still run and cool, but it's got mechanical contactors. You know, they work, but then old technology, you can't get the controls anymore. If the compressor failed, you can't get it in. So people tend to change their IT cooling equipment on a more regular basis, simply because the technology is increasing and increasing and increasing.
More data, more kit in the small.
It can be. Sometimes, you know, it used to be that it was 400 watts a square meter. Then it went to 750. Then it went to 1,000 watts a square meter. Then to 2 kilowatts a square meter and 3 kilowatts. Now they're talking of 5 or 10 kilowatts a rack. You know, so you know you can't put enough floor grills in the floor to get the air in. So hence it's going to liquid cooling technologies. But there's so much opportunity to make existing facilities better by spending really quite a small amount of money. But it does come down to the client as to what they want to do and how they want to play it. But
I'll keep quiet now.
yeah, as I say, you know, that there's I mean, there's a few, there's a lot of opportunity out there, but it does come down to being very polite to the customers, to the clients, because sometimes they know what they want, sometimes they don't. Sometimes they can be wholly realistic, sometimes they can be wholly unrealistic. And you know, you can't fit a quarter of a pint pot. You know, you can only have so much power. You've only got so much space. You can't fit that heat rejection on that wall or on that roof. You know, you've got sometimes a dose of reality sometimes is required when we come and look at jobs. And then on the other side of the coin, as I mentioned earlier, you'll have a customer that's got 500 kilowatts of IT load newly installed. In fact, they've only got 77 kilowatts of IT load because they've reduced over the years and they don't need as much cooling. So you do find both sides of the coin.
Do you work in the health sector?
Sorry?
You work in the health.
We do work indirectly in the health sector in that we work with people who build the cabins. So for standalone edge data center, UPS, IT, additional infrastructure, where they'll do a 40-foot container and it'll be around the back of the car park of the hospital as ancillary IT, because their IT in their room in the basement is full and they need more. So it's easier for them to bring something else in, put power and bring their fibre in, and then run that as a separate standalone. We do that for universities as well. And then we work in data centers where they're putting in opening new suites as clients are coming in. You know, some of the places you go into are so pristine and shiny and new, and then you'll go into others where they've got the old floor tiles where they've drilled holes to let the air in. So they haven't even got proper grills with it's you see all sorts, and you know, it's how they do it and how they want to invest. But yeah, I say I hope that's been of interest.
A lot of
interest. I've got some cards. I've also got some USB sticks with all the brochures on. I was going to bring you some pens, but I can't find them. So I think we've just had DCW down at London. So I think all the pens went, but if I give you, I've got no idea what the capacity of them. So by all means, feel free to wipe everything that's off them and use them for your own devices. But as I say, there's brochures are lovely in as far as they go. It's always better to ask if there's anything that you need in terms of selection. That's what we're there for, to provide all the information. So feel free to contact as you need to, basically.